All right, one more circuit reduction problem. And so we're going to look at reduce the following. What I want to find out is what is EO as a function of EI. And here we have resistors and inductors, so we got to use impedance to reduce this down. All right, first thing we'll notice, here, look from here to here and here to there. The voltage at EB is the same as the voltage across this resistor EO. So EO equals EB. All right. So that means I can take all of this stuff, whatever EB is, and replace it with one impedance now. And so we know what that is. Now, once I get this, we'll see that relative to the voltage of EA, these two and then this big thing, they're all in series. So the voltage from here through all of this mess is equal to the voltage across this half ohm resistor. And we'll call all of this piece here ZEQA. So the equivalent impedance from there back. ZEQB is the impedance from there back. All right. So we've made one observation. Let's get to work. So the first thing to do is combine all this stuff, simplify that down. That's going to be called ZEQB. And so if I look at this, I have 1/2 ohm in parallel with a 1/2 Henry and a 1/5 of an ohm in series. Okay, so 1/5 of an ohm plus 1/2 Henry, they add together. Okay, that's the impedance across here, but it's in parallel with this. So I take this impedance, take 1 over that, plus 1 over a 1/2, and do a little math, and you get the following. I'll leave that to you to check. So now I have the equivalent impedance of this whole piece, and so next thing I want to do, and so that's, anyway, IB times this whole piece is EB, E0, the output, or EB, whichever you want. So next thing I'm going to do, I'm going to actually do this all in one shot. I'm going to get the voltage. I'm going to get this equivalent piece in here. So what have I got? I've got this in series with all of ZEQB, this whole thing. And so this plus all of this is in parallel with that. So look what I have here. They're in parallel. You go 1 over all the impedances. So 1 over a 1/2 plus, what's all of this? It's this in series with all of this. So the impedance, or like a resistance of a capacitor, is 1 over CS plus all of this impedance in series. We add them, but then we add in 1 over that. Okay, and then all that adds up. And okay, C, keep in mind this is 2 microfarads. Okay, so if you put that here, that 2 microfarads, 2 times 10 to the minus 6, that becomes 500,000 over S. And then we have this -1 here. You got to remember that. Okay, you reduce this down. I'm just going to call all of that ZEQA. All right, so we have expressions for ZEQA, all of this, and ZEQB, all of that. Okay, so let's see what we can pull out. The next thing I'll notice, if I know this is all of this impedance, I can say 1 plus all of this impedance is the total impedance in the system. So impedance times current is the Laplace transform of voltage. So I have ZEQA, this piece, plus 1 ohm, brackets, times IA, whatever this current is EI. And that would be EI of S. All right, so here's the next step. I'm going to make another big move. So I can express the current going through all of this relative to the input voltage. So now look at this equation. The current going through this and then all of that times this impedance is EA. Okay, we can just add this out here, EA of S. Okay, likewise, all right, let's see here. We have IA whatever that is, times this whole thing, ZEQA, okay, which we have right here, this is also EA. Wow. And I should write, well, there it is, ZEQB. All right, so IB, current, times all of this plus all of that equals IA times this, all of this impedance. So those voltages are the same. Well, now I can solve for IB relative to IA. So IA, whatever the input current is, which is equal to EI divided by 1 plus ZEQA. Here's this times this divided by this impedance. This here is what's, I just put the numbers in. Okay? Divide through. Divide this through, and so I have IB is IA ZEQA divided by all of this. Okay? Well, now I can substitute in for IA, this input voltage divided by all of this. It's kind of like a little puzzle. Stick that in there. Well, then I would have IB relative to EI. So that's this piece right in here. So if you look at what we have here, just ignore that for a minute. I'm just going into here, and for IA, putting in this piece. Okay, but that's IB. But IB times this is EO. So I add that on. So I have IB times this impedance gives me EO. And we have answered the question. We'll move on to coupling with magnetic fields next.